All right, perfect. So it's been 4 years since I stood on this stage. It's been 18 years since I first came to Devoxx, and it's been an amazing ride. It's amazing how much Java has evolved since then. When Stefan did the little poll about what version of Java people are using, someone mentioned where's 21. So how many people here are using Java 21 already? I see a few hands go up. I'm happy to see a few hands go up. I'm not surprised to see a few hands go up. We've been hard at work making more Java, and the latest version, which was been available 2-3 weeks from now, is very compelling. A lot of good features in it, so I can understand why people have jumped on it. Before I talk about Java 21, I want to talk a little bit about where Java comes from and how we've been able to deliver Java faster. So that means we have to talk about some old news. I hope I won't take up too much time on this. Last time I was here, we were just starting out with the new 6-month release cadence. So it was Java 12, Java 13 timeframe. And so you all remember the bad old days, the way we used to do things. We had a feature boxed release model. Releases ran 2, 3, 4 years. There were often delays. There was not that much predictability. And because the trains were so infrequent, there were a lot of costs that this generated. We had to have a very heavyweight and expensive planning and release management model, which meant engineers spend time doing planning work and not doing feature work. And again, because the trains were so infrequent, there was this irresistible temptation for a feature that maybe you've been working on for 3 years that's like almost ready, and there's this temptation to convince yourself, well, no, it actually is ready. We're going to put it in because no one wants to wait 3 more years for their feature to ship. And the result was the release model was creating a lot of distortions for the way we work and for the quality of the product. And it really wasn't working for anyone. It wasn't working for developers who had to wait a long time to get the features they wanted. It wasn't working for enterprises who really just wanted stability, and things like late integrations reduced the stability of initial GA releases. Backporting a lot of things also reduced the stability of releases. And it wasn't really working for us as JDK developers either. So, we took a hard look at the problem and decided we had to do something. And, we asked the ecosystem and our customers what they need. And of course, in an ecosystem as large as Java, it doesn't speak with one voice. But surprisingly, there were 2 very clear voices that came out when we asked, what do we need to be doing? There was the voice of developers, and developers were very clear about, we want features faster. We want features delivered faster. We want more predictable releases. We want to know when things are coming. And enterprises were also very clear, we want stability. Once we put an application into production, we want a stable version of the JDK that we can deploy on, that we know gets security fixes and critical bug fixes, and absolutely nothing else. Because backporting features risks the stability. And the old model we had was making precisely no one happy. Developers weren't happy, enterprises weren't happy, the people who work on the JDK weren't happy. So we revamped our model. And not surprisingly, if you have a customer base where there are sort of 2 clear customer profiles of what people want, the structure of the answer is going to have kind of 2 things in it. So we switched to a model which we call tip and tail. The tip releases are time boxed every 6 months. Features are integrated when they're ready. If you miss the train, that's okay. There's another train coming in 6 months. And then, of course, we offer long-term commercial support on selected older releases, the tail releases. And these get security updates and critical bug fixes only. And that makes sure that they're stable. Once you put an application in production, you don't have to worry about things changing out from under it. Now, everyone was skeptical at first. People both inside the house and outside the house were skeptical. Folks working on the JDK said, this is crazy. We could never do this. We're never going to be able to run a release in 6 months. We're going to get eaten by process overhead. What if we don't have anything to ship? It'll be so embarrassing. And it turned out that these issues were not really issues. They were just fears. And the ecosystem was even more skeptical. In fact, some of the people in this room made blog posts about how ridiculous our new release model was. I have the pictures. A- a lot of these, surrounded on denial that there was more Java to make. Java 8's all I'm ever going to need. Or, we can't possibly adopt a new release every 6 months. And the reality is this is all that change is hard. And we fear change, and so we resist change. So, when we talk about change, we're not just talking about changing our release model, although we did. We really had to change our mindset. We had to change the way we think about developing features, and kind of unlearning the 20 years or so of experience and muscle memory that we developed in building Java over those previous decades. And in particular, one of the hardest things I think for a lot of people on the team to really get was it's okay to miss the train. If your feature's not ready, that's fine. There's another train in 6 months. Your feature will be ready. People will be happy to have it when it's ready. We had to break ourselves of the habit of backporting everything. I'm really glad we did that. But it also really changed the way we design features. And this has been a little bit of a surprise for us. So features that used to be developed as big monolithic features and delivered in one block, we've learned how to break up into smaller but still standalone features. And this has worked out really, really well. The big hidden benefit, which most of you don't see except indirectly, is the amount of time that JDK engineers spend in release meetings has gone almost to zero. And I won't tell you how much it was before, but the answer was way too much. And if developers are spending less time in release meetings, less time doing backports, they can spend more time working on new features, and that shows up as a faster pace of progress. And all the features in Java 21, that I'm going to talk about, we would not have been able to develop them as quickly and effectively. So, this process has been a huge success. I think it's worked out better than we could have possibly hoped it would. We were able to slash our release process, like I said, almost to zero, because we had reduced the release risk so much. We were able to slash the number of backports we did because they just weren't needed anymore. All of this meant more stability for LTS releases, made people more confident in adopting releases the first day they were out, rather than saying, oh, well, I'll wait a year and see what happens, which is what people used to do in the 6, 7, 8 days. And again, all of this means more time to spend on development, and that means more features. So I'd like to say everyone is happy. I've been in this industry long enough to know that no one's ever happy, but let's just say everything is awesome, okay? Developers get features faster, delivered earlier, more rapidly, with more predictability. Enterprises get supported stable releases with security and critical bug fixes. JDK developers get to spend more time developing, and the predictability of the process and the repeatability of it reduces everybody's stress level. So, this transformation was a, absolute huge success. I wouldn't ever want to go back to the old way. And at the same time, our feature pipeline is, better than it ever was before. So this was the enabler for getting to all the cool features you came to hear about. So let's talk about features. So here's the list of the features that are in Java 21. This is actually just the JEPs. Obviously, there's way more to a release than just JEPs. Every release has on the order of 1,000 small improvements, performance improvements, new methods and libraries, bug fixes, things like that. And this is just the list of JEPs from Java 20 to Java 21. So there's just the features that are in Java 21. They're spread out over a bunch of areas. We have new language features. We have new library features. We have new runtime features. If we zoom out and we look at what's come in since Java 17, it's a slightly bigger list. It's not hugely bigger, but it's slightly bigger. If we zoom out a little bit further and look at the features since JDK 11, it's you can see that we've been busy. And it's a little bit of an unfair comparison because it was 3 years between 11 and 17. At that point, we reevaluated and decided to switch to a 2-year cadence for LTS. So 17 sort of had 3 years to gestate. 21 had 2 years to gestate. So there's quite a few items in blue, but you get the point. We've been busy. So JEPs are how features get delivered into the JDK, but they're not necessarily how features get built. Features get built in projects in the Open JDK community. And these projects sort of represent the choices that we make about what we're going to invest in. So a project may produce one JEP, it may produce many JEPs, some produce no JEPs. And each project sort of has a theme area, and it has an underlying reason for being, which is almost always a pain point where we see developers working too hard to do something that should be easier in Java, or sometimes we get a nudge from the competition where we see, oh, okay, well, Julia is doing better than Java in GPU computation. We really should catch up with that. And we know that Java is not going to be the best thing for everything, but we want Java to be good for all of these things. We don't want to ever give people an excuse to not use Java. And Stefan had some good examples of using some of the newer features from 22, including preview features. The vector API and the foreign function interface to do his little to do the AI demo. So these are things where we looked at pain points people were experiencing 3, 4, 5, 6 years ago, and identified what is it we can do to sort of raise up the platform and make it a better place for for these kind of things that people want to do. So let's talk about some of the features in JDK 21. The big news, obviously, is Loom. Project Loom has gone final. I sort of think Loom is going to be the lambda of JDK 21 in that it's going to be the real impetus for people to to upgrade from what they were doing. Obviously, this is a subject that's near and dear to my heart. Loom sort of takes Java concurrency to the next level by barely changing it at all. And this was really an amazing move. So why did we have to do Loom in the first place? Well, Java has had threads since day one. This was one of the things that distinguished Java amongst other programming languages at the time that it came out, was that it embraced concurrency and had an integrated cross-platform concurrency model and memory model from day one. And threads are great. Threads are what allow us to do lots of things at once with readable sequential code, with full support from the language in terms of using the control flow operators the language gives you, using the error handling mechanism the language gives you, giving you comprehensible stack traces, being friendly to operating systems. Threads are great. But unfortunately, threads are a little bit heavyweight. Threads are generally created by the operating system, and they're expensive to create. They drag around megabyte scale data structures, and most operating systems will only let you create a few thousand. And this means there's a sort of a collision course between the comfortable thread per task programming model, which lets us write readable sequential code, and wanting to use the machines efficiently. Some people were, in the last few years, been reaching for reactive async frameworks, which offer better scaling, but those frameworks come at a very significant cost. The programming model is awful. They're hard to debug. Stack traces are incomprehensible, and we knew there was a better way. So we wanted to stop putting developers in a situation where they had to choose between being efficient developers and efficient users of computing hardware. So the answer that Loom has for this is what we call virtual threads. And the answer is simply, well, if threads are too heavyweight, make them lighter. Well, that sounds easy, right? That sounds like one of those people who say, well, I would just write a program with no bugs in it. But the thing is, we actually pulled it off. So virtual threads are real threads, but they're much lighter weight because they don't drag around these huge megabyte scale data structures. They store their thread stacks as delimited continuations in the garbage collected heap. The stacks are pay as you go, so the smallest, when you start a virtual thread, you're paying maybe a couple hundred bytes. And these things can scale to like 1 million concurrent connections on a laptop like this one. But they're not some other weird abstraction. They're real threads. They implement Java lang thread. They support thread local. All your thread code just runs. You get clean stack traces. You get clean thread dumps. You get all the things that you would expect from Java. You get single-step debugging and profiling. All your code just works. And the point of this is not to make your application go faster. Virtual threads won't make your your code go faster, but it will make it scale better. So in most server applications, most requests spend most of their time waiting on I/O, I/O on a socket, I/O on a file, I/O for the database. And if we program with a comfortable thread per task model, and most of those tasks are waiting on I/O. Eventually, we're going to run out of threads before we run out of CPU, and that's because we run out of threads because we run out of memory. And this effectively raises the cost of deployment because we're using a lot of memory and we're not using the CPU resources very efficiently. So this graph kind of visualizes what the benefit is. We have some IO bound tasks in a thread pool. So the blue line represents a thread pool with 200 threads. When load gets presented on the application, latency is fine until all the threads are busy, and then latency falls apart. If you say, oh, well, let's just put more threads in the thread pool, that's what the green line represents, or I guess the light blue line represents, and that gets better, but again, it has the same behavior. You hit the bottleneck of how many threads can I have before you run out of CPU, and latency again falls off a cliff. The virtual threads line, you can barely see it. It's the green line that's running near the x-axis. It's going to keep going until you run out of CPU. Eventually, it'll fall apart, but like somewhere over there in the next theater. So virtual threads, are designed, to model a single task. They're not designed to model a mechanism for running tasks. So we need to unlearn a little bit of what we've learned about concurrency. There's a lot of intuition that we've built up about concurrency over the last, however many years that we're going to have to unlearn. For example, we've learned that we're supposed to pool threads. Well, virtual threads, you should definitely not pool them. They're so cheap. Just make one when you need one. Make one for every task. Make one for every async, operation. But we think that this will obviate the need for people to to use async reactive frameworks. You don't need to change paradigms. We just needed to make threads better. So the surface change for Project Loom and virtual threads is actually quite small because the virtual threads implement the Java Lang thread class, but under the water, a tremendous amount has changed. We had to do a lot of work to retrofit basically every blocking operation in the JDK to be aware of virtual threads. And when code running in a virtual thread blocks, we suspend the thread, passivate its stack to the heap, and bring in, ask the scheduler to bring in another virtual thread. This all happens transparently. It's all under the water, but there was a tremendous amount of work in the JDK to make all this possible. And Alan is going to talk about this tomorrow at 1:50. One of the really cool things about Project Loom, I think, is going to be kind of the sleeper feature of Project Loom, is that it's an enabler for sort of a new paradigm for concurrency, which is called structured concurrency. This isn't something we invented. This is something that's been experimented with in a lot of other language communities, the Python community, the C++ community. And it's a really simple concept. It's like so simple, it makes you wonder, why didn't we think of this years ago? Which is, if you have a control flow that splits, it should rejoin with its children in the same lexical scope. In other words, parents should wait for their children. Seems like a reasonable thing to do. The benefit of this is that it makes all the things that are really hard with threads. So if anybody's read Chapter 7 of Java Concurrency in Practice, most difficult chapter of the book. It's on cancellation and shutdown. Also, probably the least satisfying chapter of the book from my perspective, because there wasn't a lot of science there. There were just a lot of tricks for how to get things to work. This is the science that was missing, is having a discipline that allows task management to be compositional, and it makes things like deadlines, timeouts, error handling just absolutely trivial. But it only makes sense because threads are so cheap now. I'm not going to go through the code example. Alan will do that tomorrow. But there's also in preview a simple API for structured concurrency in JDK 21 as well. But I'm really excited about this. All right, so I'm going to switch topics a little bit. I'm staying on the topic of runtime and performance. I want to talk about some improvements in the Z garbage collector. So the Z garbage collector was introduced in JDK 15. How many people here are using ZGC? Few people. Okay. So how many people hate garbage collection pauses? All right, so some people should look into ZGC. So ZGC is a new garbage collector that supports terabyte scale heaps with sub-millisecond garbage collection pauses. And these pauses don't scale with heap size or live set. And as you would expect from a modern garbage collector, it has almost all the buzzwords: concurrent, parallel, region-based, compacting, NUMA aware, blah, 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 blah. But the upshot of it is we pretty much don't have to think about GC pauses anymore, which is kind of what we've been hoping for 30 years. So sounds great, right? What's the catch? Well, there's a reason we have so many garbage collection algorithms, and that is that garbage collection is always a trade-off. It's a trade-off between latency and throughput and memory utilization and predictability and locality and any number of other things. So there is a cost. Applications running ZGC take about a 2% throughput hit compared to G1, which is pretty small if you care about pauses, and probably not so small if you don't care about pauses. So we're not getting rid of the other collectors. It also uses more memory, but again, if you really care about predictability and latency, ZGC may very well be a good alternative. I have some data here on pause times that were taken from the Spec JBB 2015 benchmark, running G1 and ZGC, looking at average and P95 and P99 latencies. And the G1 latencies are in the realm of 300, 400, 500 milliseconds, and the ZGC, well, we can't see those. Okay, so let's zoom in, switch the scale off to microseconds instead of milliseconds, and scroll down. Hi, Duke. And we see that for the same benchmark, the ZGC numbers are on the order of a couple hundred microseconds. And like I said, these don't scale. They in this case, not scaling is a good thing. These don't. If you have a larger heap, pauses don't get bigger. If you have more live objects in your heap, pauses don't get bigger because it doesn't actually do any GC work during the pause. ZGC, like I said, has been part of the JDK since JDK 15, and in JDK 21, we've improved it to add generational capability. So the one buzzword that was missing from that buzzword list that I went through very quickly was generational. So the original ZGC was single generation. In JDK 21, we've added generational capability to ZGC. The upshot of which is one of the trade-offs that I mentioned, which is using more memory, has been vastly improved. So, for example, we took the Cassandra benchmark and found that for the same amount of throughput on a single machine, we were able to see 75% reduction in memory utilization, for the same throughput. So ZGC is great, getting better with every version. The other collectors we're not ignoring either, right? So if you're using G1 or you're using Parallel, these are also continuously under improvement. This again, same benchmark, Spec JBB 2015. Big improvement in throughput from 8 to 17, somewhat smaller, but still non-zero improvement in throughput from 17 to 21 as well. All right, another thing that's been going on for probably 6, maybe 7 years at this point that is coming to fruition is Project Panama. These are the technologies that Stefan was talking about in his AI demo. Project Panama is about, or at least in part about, better access to native memory, that's memory outside the Java heap, and native code, that is code that that isn't managed by the JVM. Now, if you've been programming in Java for a long, long time, you'll remember that we used to discourage native code. There was that branding campaign about pure Java, and pure Java was great, and all of that. And that's true, but there are some great native libraries out there as well. And they're not going to get rewritten in Java, and they shouldn't be rewritten in Java. So if you're doing off CPU computation with CUDA, or you're doing graphics with OpenGL, or you're doing linear algebra with BLAS, you should be able to just use those libraries from Java, and it shouldn't be as painful as it is now. So you can do those things today, but it is painful. How many people here have used JNI? Wow, I'm sorry. So JNI is awful. A lot of you know this. Some of you are getting the idea. You have to code in this horrible combination of Java and C. It's difficult to maintain. It's super easy to make mistakes for which you get very, very poor error feedback, except, oh, I crashed my JVM. Right? So that's not the good programming experience we want people to have. And similarly, the experience of programming with off-heap memory, not quite as bad as it is with JNI, but byte buffers are not fun and unsafe isn't great. Byte buffers are limited to 2 gigabytes. They have all kinds of limitations, and unsafe is, well, obviously it's unsafe and it's eventually going away. And so Panama has been built, from the ground up for both safety and performance. So you get highly optimized bounds checking, both spatial and temporal bounds checking, so protection against buffer overruns, protections against used data for free, but in a way that these checks get hoisted away and optimized away by the compiler routinely, so you're not really paying anything for them. And the programming experience is also a lot more pleasant than that of given by JNI or unsafe. Panama isn't quite out of preview yet. It's hopefully in its last preview in 21. We'll go final in 22. I know I'm not supposed to say things like that, so pretend I didn't say that. But it represents a big payoff from investments that we've been making over the last decade, because it's built on investments we've been making in the JVM, method handles, var handles, to get a lot of the performance it gets. And so years ago, when we said eventually unsafe was going away, well, we're not going to do that until there's a safe supported alternative. Panama is one of the vehicles that are bringing us safe supported alternatives for unsafe. What we really hope will happen with Panama is that people who maintain native libraries or others in the community will routinely wrap these native libraries with good Java APIs and distribute those with the library or separately from the library, so that Java developers don't have to do that themselves. And so if you want to hear more about Panama, there's a couple of talks from Oracle folks. Per is talking about form and function and memory access on Friday, and Jose is talking about SIMD programming with the vector API tomorrow. All right, so let's talk about something a little bit closer to what I personally work on, which is the Java language. Since I last stood on this stage, here are the JEPs that Project Amber has delivered or is working on. So we've been busy. In case you don't know, Project Amber is sort of the umbrella project for these small productivity-oriented language features, although some of them are not small. But unlike some of the other projects in OpenJDK, it's an ongoing project that keeps pumping out good stuff, whereas most projects sort of have a goal, they eventually deliver, and then they wrap up. So this is a long list of things. They may look like a grab bag of whatever we were interested in working on in the moment, but there's actually a cluster of these features that kind of work together. So each of these features stand alone. They're standalone features, in their own right, but they were designed to work together. They were designed together, and they likely would have been one big feature under the old release model. And I don't have time to go through all of these features or even any of these features right now. I will be going through a lot of these features in my language futures talk on Friday, but I do want to just give a code example to give you a flavor of how all of these features have come together to make programming in Java more pleasant. So the theme of the features that I highlighted in blue and why they're sort of all part of the same the same family is making Java better about working with data. These features are all about modeling and processing plain data. So records and sealed types give us algebraic data types. Pattern matching gives us a much more pleasant way to do visitation over algebraic data types. So visitor without the visitors, and a bunch of other language features have been upgraded along the way to make this easier. And why are we doing this now? Well, the way we program has changed. 15, 20 years ago, we wrote these big monoliths that were Java end to end. Even if if programs talk to each other, they exchanged serialized Java objects. The whole domain model was defined by Java objects. But today, program units are smaller. They're not all written in Java. Very often, our domain model isn't defined by Java objects, but by untyped data like JSON or YAML or SQL result sets. And we need a better way of dealing with plain old data that we can convert to and from the wire and still get the benefit of Java's strong static type system when you're working on it in your program. So here's an example of these features sort of all put together. So textbook example, modeling an expression where we say an expression is either the sum of two expressions or the product of two expressions or the negation of an expression or a constant, right? Everyone's seen this textbook example. And if we want to evaluate this an expression, well, there was kind of a hint there where I said an expression is this or this or this or that, so we're going to have to deal with all the cases. And we're using sealed types and records to model this domain. So the sealed type is the part that's enforcing an expression is this or that and nothing else. And then each of the alternatives is modeled by a record that allows us to strongly type what each of those cases are. So a sum is the sum of two other expressions. A negation is the negation of one other expression. And if we're going to evaluate an expression, we can say, all right, well, we have an instance of a sealed type. Let's switch over it. I can use record patterns to deconstruct each of these cases. If it's a sum expression, then get me the left and right sub-expressions, evaluate each of them, add them together. That's the result of evaluating this. Same thing for product, negation, evaluate the sub-expression, negate it. If you guys remember, the last time I was here, the keynote that I did, actually the year before that in 2018, I showed this example as well, but it was all fantasy. It wasn't working yet. This is all now working in Java 21. So the story that we've been telling for the last few years is being delivered. And this, there are like 6 or 7 features, each of which have their own JEP, that are represented in this code. We have switch expressions, we have sealed types, we have records, we have patterns and switch, we have record patterns. Notice we don't have to have a default clause in the switch because the compiler knows that an expression is a sum or a product or a negation or a constant, and you've covered all the cases, and so you don't have to have a default clause. In fact, you don't want to have one because you want to engage the strong exhaustiveness checking that the compiler can give you. So as a little touchstone for how are we doing on improving Java, I always look at how some of these examples might be written in other languages that people point to and say, that's how I want to do it. So if you're wondering what this looks like in Haskell, well, it's not all that different. It's about 4 lines shorter. 3 of them are empty closing braces, so I think we're doing pretty well. Okay, I'm not going to go through the Haskell code. A couple other things that we're doing that don't always show up, on the JEP list is we really want to make we're making a big investment in where is the next generation of Java developers coming from. We want to make sure that students have a good experience learning Java, and Stefan did the IDE survey about what IDEs we all use. IntelliJ was top of the list as expected. I've been using IntelliJ for 20 years, and I think it's probably the finest piece of software I've ever used. So we as Java developers are very lucky with our IDEs, but not everybody wants to use a Java-centric IDE. And in particular, a lot of schools are using lighter weight IDEs like Visual Studio Code because it runs on the Chromebooks that students are using, and it supports all the languages that that they want to teach in. Until now, there hasn't really been a very good Java environment for Visual Studio Code. There is one, but it hasn't been very well supported. And so we're announcing Oracle is distributing a platform extension for VS Code that's based on the NetBeans work, which is in turn based on the JavaC compiler. So it supports all Java language features out of the box, including preview features, has great interop with build tools and testing framework, and should be in the VS Code marketplace maybe this week. So if you use VS Code, you should definitely check this out. Similarly, in terms of reducing the bar for access to Java, we've launched the Java Playground at dev.java, which is a browser-based REPL based on JShell. So don't have to install even an IDE or a JDK. Just can open up a web-based JShell and start playing around. All right, so I want to switch gears a little bit and talk about safety. So when I learned to drive, seatbelt use was not required in the U.S. It was optional. Then pretty soon after that, the regulations came along, and most people took this as a helpful nudge of like, okay, yeah, I know it's good for me. Okay, I'll do it. But there was also a vocal minority, you might know some of these people, who chose instead to use this as an opportunity to complain about governmental overreach and intrusion on personal freedom and all of that. But 30 years later, the statistics are really clear. Most people wear their seatbelts, and a lot fewer people die on the highway. So I bring up seatbelts because we've used the seatbelt metaphor before. When we did modularity in Java 9, we described it as a seatbelt, not a jetpack. But the analogy was kind of lost at the time because at that point, there really were no jetpacks in evidence. There were just seatbelts, and no one really wants to put on their seatbelt when they're not moving. But the seatbelt of Java 9, which is that internals can be actually kept internal, that platform internals can be evolved, isn't there because we want to wag our fingers and say, keep out of our code. It's there because we want to move faster. So in the early days of Java, most boundaries like access control were really more like suggestions than requirements. And a lot of libraries took advantage of this flexibility and did some very cool things with it. But it didn't take very long before this started to be a drag on our ability to evolve the platform because we couldn't freely evolve our internal implementation. And I know personally, in the Java 6, 7, 8 timeframe, this was a real problem. This was really slowing us down because you would do something that seemed harmless, like turning a private field of some non-public JDK class and make it from mutable to final, and that breaks some library because they're breaking in with with set accessible and binding tightly to platform internal implementation. So we left that in the past with Java 9, and the rapid pace of innovation that I'm talking about today is the jetpack that we were promising then. Loom is the jetpack. ZGC is the jetpack. And it's nice to think that maybe we can have jetpacks without seatbelts, but the reality is we could not possibly have delivered these features so quickly, so reliably, so effectively without the seatbelt. So, by writing in Java today, your application gets a steady stream of improvements tomorrow, delivered incrementally and compatibly, and you can upgrade to Java 21 and get all the benefits of ZGC without changing your code, or get the benefits of Loom with making small changes to your code. That is, if you can upgrade. Now, I hear you thinking, wait, what are you talking about? Java is all about the compatibility. Why is the ability to upgrade even a problem? Well, it's a problem because of dependencies. We all have some direct dependencies in our applications, and those dependencies invite their friends, and we have some indirect dependencies. And most of the time, these libraries have no trouble upgrading to the latest JDK, but a small number can't because they're dependent on unsupported platform internals. And it only takes one dependency to keep the whole application from being able to upgrade. And that might be a library that you'd never even heard of. You didn't even know it was part of your application. It was just one of the libraries that you use invited it along to the party. So the good news is the jetpacks are going to keep coming. But I think we have a challenge ahead of ourselves, and one that we have to navigate together as a community, which is how do we manage the transition to universal seatbelt use so that we can all ride the jetpack and do so safely. And so the challenge that applications are seeing in upgrading it generally comes from a small fraction of libraries, and usually those libraries are using APIs that were restricted or removed in later JDK versions. And we don't remove things gratuitously. We do it very carefully, we do it very slowly, and when we do, there's almost always a safe, supported alternative. And we saw an example of this earlier, which was off-heap memory access through unsafe. People are doing that with unsafe now, and that's being replaced by a better alternative from Project Panama. So replacing something with a better something should be a good thing, but it puts libraries that use the old unsupported API kind of in a bind because it's hard to support both the old way and the new way in a single code base. But the problem isn't that something got replaced or removed. The problem is the libraries are still clinging to the old release model. So they're trying to have one code base that's one size fits all. They're trying to have one release train for everything in the name of convenience. But this is often a false economy and causes friction elsewhere in the ecosystem. And as the JDK moves faster, the greater the impact of this impedance mismatch is going to be. And so if we have an impedance mismatch, obviously the solution is let's eliminate the impedance mismatch. And so I'm sort of issuing a challenge to the Java ecosystem, which is think about aligning to the tip and tail model that has been so successful for the JDK. This is actually really simple to do. You have a tip version that's baselined on a relatively recent JDK version, probably an LTS, could be 17, could be 21, I don't care. And you have a LTS train that's baselined on some older LTS version for that's going to receive critical bug fixes and security fixes only. And this split really benefits everyone and would benefit everyone even more if libraries adopted the same release model that the JDK did. So developers who want the latest features, they can use the tip of the JDK and the tip of their libraries. Enterprises who want stable deployments can use the LTS of the JDK and the LTS of these libraries, and the ecosystem would be aligned around a single model. Now, it sounds like I'm exporting a bunch of work on the library maintainers. Who here maintains an open source library? So it sounds like I'm making more work for you guys, but I'm actually making less work for you guys. This is so much easier than it looks. And it's probably so much easier than what you're doing now. And we're starting to see some green shoots of this in the ecosystem, that forward-looking libraries like Spring are starting to adopt this approach and I think are having good results with it. So I would expect to get all the same skepticism that we got originally when the JDK switched release models. But I'm here to tell you, I was wrong about it then. I was giving all those same excuses about, oh, this will never work, that everyone else was, and boy, was I wrong. And those objections were largely based on the misperception that, oh, it must be more work to do it this way. In reality, it's less work to do it this way. If you have an LTS and you're only backporting the most critical bug fixes, maintaining an LTS isn't that hard. If you have a tip that's baselined on a latest JDK, well, you get to use all the cool things in the latest JDK. That's going to make your development easier, faster, and a lot more fun. And so, the problem is not that the JDK is changing. The problem is that libraries are trying to have a one-size-fits-all release model where they're supporting JDK 8 and JDK 21, and that's forcing them into a least common denominator, which doesn't benefit anybody. When a library says, I only work on 8, you're basically saying, my users have to choose between my library and ZGC, and that's a bad choice. We shouldn't put people in that choice. Okay, so I'm starting to wrap up here. I want to do a little bit of a look ahead at something that we've just started working on recently, which is Project Leiden, which is about improving startup and warm-up of Java applications. And historically, Java has favored long-term peak performance over startup, which historically was actually a really good trade-off for applications that ran for months and months and months. And as a result, Java does a lot of work at startup, parsing class files and interpretation and JIT compilation, profile gathering, symbolic linkage of call sites, things like that. And so the cost of the trade-off that we made is that startup and warm-up for short-running applications can suffer. And of course, we want Java to be good for everything, so we don't want to just say that's the way it is. We want to give people some good choices. So here's a a way to think about startup and warm up. If you have an application that is like doing a task repeatedly, you expect the first iteration of your task to do more work because it has to get everything set up, and then thereafter, you sort of approach a steady state where there's a small incremental amount of work for each task. The green line represents a sort of ideal. The yellow line represents the sort of practice. The area under the first data point represents startup, and the area under the other data points represents warm-up. So if we want to push these curves down and improve our startup and warm-up time, the obvious thing to do is to take some of that work that's happening at startup and warm-up and shift it off the critical path. This could either be later in time by being more lazy, or earlier in time by shifting work to a build time phase. And this kind of work shifting is old hat for the JDK. JDK employs many, many work shifting techniques: constant folding, garbage collection, lazy class loading, JIT compilation. These are all time shifting techniques. And so we can build on this, this approach that's sort of in the DNA of the JVM to shift more work from runtime to an earlier phase. And so, we did an experiment where we took existing components in the JDK, the JIT compilers, and the class data sharing startup cache mechanism to basically cache more things in the CDS archive than we currently cache. So currently, CDS caches things like class metadata, and we taught it how to cache compiled code and resolve constant pool entries and call site linkage and things like that. And the nice thing about this approach is no changes to your code, runs 100% of existing Java code, no loss of Java's natural dynamism. You just have to do a little bit more work at build time so that you can do less work at runtime. I have two graphs I'll show you, and then I'll wrap up. So the first one was applying this to Java-C. So Java-C is generally a relatively short-running task. Fun fact, Java-C usually doesn't get out of the interpreter. Most of the compilation you do, it's finished compiling before it has to JIT anything. So in this example, we repeatedly compiled small batches, like 100 small source files, and the yellow line was the observed time without doing anything, and the red line represents applying the techniques I talked about, which is shifting some compilation and linkage, to a training run prior to runtime. And what we saw was basically a 2x startup improvement and a significant warm-up improvement for no change in our code, just a little bit of configuration work. So that was pretty promising. And we applied the same techniques as well to Spring Boot. So this is some startup time numbers for the Spring Boot Pet Clinic application. The first bar represents the baseline, just run it on JDK 22. The blue and light blue and dark blue lines are applying various app CDS pre-computation of doing some compilation ahead of time, doing some class analysis ahead of time. And the last one folds in the Spring AOT tools, which does some Spring-specific analysis and shifts some of the Spring startup work ahead of time. And when you take all of these together, we were able to get over a 4x startup improvement. Again, no change to existing code. So these are very promising numbers, but it's very early days. I'll be talking more about this at 2 o'clock this afternoon in my Project Leiden update. So as Stefan mentioned, there are a lot of folks from the Oracle Java team here at Devoxx, as well as lots and lots of sessions on JDK 21. So I was only able to scratch the surface, very briefly in this talk. So if you want to hear more, come to these sessions this week. Thank you very much. Have a great conference.
Thank you, Brian.
Thank you, Stefan.
Thank you.